chapter is now going to start on kinetics for chapter 17. Oh, where's the text to make sure that I'm following along? All right, so when we're talking about kinetics, we're talking about reaction rates. So reaction rates. So what reaction rates are, so this is some measure of some property within a certain amount of time, right? So we'll say that it's a measure of some property um, that varies over time. So some measure of property that varies over time, right? So when we talk about rate, I think the most common one is, something like distance, right? How do we measure distance, right? Or, I'm sorry, rate. When we're talking about how fast we're going, right? Is that rate is equal to some amount of distance, some distance over some amount of time, right? And this gives us a rate, right? When we talk about reaction rates, we're measuring some property of that reaction, right? So we talk about rate of reaction, right? What we're talking about, instead of some distance over amount of time, we're talking about some property that changes. So the reactant, how much reactant is consumed, how much how much product is made. So our rate of reaction could simply just be some amount of reactant that is consumed over some amount of time. That our rate of reaction could also be, the rate of reaction could be some amount of product that's produced over some amount of time. So when we're talking about products being produced, reactants being consumed, right, is that we discuss it in a way that that's familiar to you already, and we talk about the concentration, right? When we have our reactants, we have some concentration of this reactant, right? We have some concentration of the product. During our reactions, right? The reaction decreases, product decreases, or vice versa, depending on Le Chatelier's principle, right? We're going to have more reactant produced than product produced. So our rate of reactions, if we're talking about concentrations, is that we could say the rate of reaction is simply some change in the concentration of the reactant over some unit of time, right? Whether it's hours, minutes, seconds, right? Or it's going to be some change in the concentration of the product, right? Over some unit of time. Okay, so let's take a look at maybe like a decomposition reaction. So if we look at a decomposition reaction, we can take a look at hydrogen peroxide decomposing into water and oxygen. So this is a decomposition reaction. So the concentration of the reactant, right? The concentration of the reactant is going to, sorry about that, is going to decrease, right? The concentration of the reactant is going to decrease, right? And it's the concentration, the change of some reactant over some unit of time. So we could say since it's decreasing, we're going to have some negative change there. So the negative change in the concentration of hydrogen peroxide over some change in time, right? So when we're doing the change in concentration, we always do final minus initial. Final concentration minus initial concentration, final time minus the initial time. So we can take a look at this and we can say, okay, so it's going to be the hydrogen peroxide final concentration minus the hydrogen peroxide initial concentration over some, I'll put time here, time final minus time initial, right? So that's what this represents here, right? And because this reactant is going to be decreasing, we cannot forget this negative sign here. That's really going to mess up your calculations. Uh, so let's take a look. So I'm going to need the textbook for this, but I will flip back and forth. I believe it's 8. Nope. Let's see. It's around this page. Yep, there we go. Somewhere around here. We should have a table here. There we go. Right. So we do see some this cough this morning. Right. So we do see some changes in concentration here. Right. Is that we have some initial time of 0, some initial concentration, and then we have the change of concentration. So we have a initial concentration, final concentration, and we're using the final concentration. You notice the negative signs there, right? So we're always losing that amount. So here, that's why we put in this negative sign here into our reaction, because we don't use negative concentration. We just put a negative in front of that problem so that we're not worried about losing that much concentration. So let's see if we can figure something out here. So we'll go from um, which one should we use? I don't want to use the one in the example here. So let's use a different one. So we'll go with, which one did they use? They use the first one and the second one. How about we use the second one and the third one? So we'll say our initial concentration is going to be 0.500. So we're going to have hydrogen peroxide. I'll put final here, and I will also put initial. I'll just use a little sub I here so we can get these values right. So my initial concentration is going to be 0.500. 0.500. And my final concentration is going to be the 2.50. Initial concentration 2.50. And what I'm looking at, I'm not looking at the, here we go. I'm not looking at this over here as my final concentration. We don't use negative concentrations. I'm using the second trial at 6 hours and the one at 12 hours. So my initial concentration is 0.500 and my final concentration is 0.250. Okay, I'm not using these negative symbols. That's how much I lost. But hey, knucklehead, I'm teaching here. Come on. All right. So I'm using these as initial and final concentrations. Come on, get off the bed. Go on, go on. All right. So let's go. And then we're using 6 hours and 12 hours. So 0.250. So my time final, time initial, my initial is 6. My final time is going to be 12. And this is in hours. All right. So as we set this problem up, it is going to be negative final minus initial. And make sure you're using parentheses because there is going to be a problem if you do it this way. Um, so let's see. So it's going to be final minus initial 0.250 minus 0.500. If you plug it into the computer like this, you're going to get a wrong answer. So make sure because here, right? So make sure that we're solving the problem here correctly, um, right? Over final minus initial 12 minus 6. And this is an hour. So I should put, let me put units in here. This is going to be moles per liter minus 0.500 moles per liter. And this is in hours. All right, let me get my calculator. 0.25 minus 0.500 divided by 12. And we get an answer of 0.0417. And this is going to be in moles per liter per hour. So there's different ways you can write these units here. Any one of them is going to be acceptable. You could write it as moles per liter, and you can put -1, and then you can put hour -1. You could also put moles. I often do this here, moles per liter per hour. That's also acceptable. Any one of those are going to be acceptable for the answer here, as far as the units are concerned. But let's see if that matches up. So let's see if that matches up to what we had here because we were given uh, that rate here, and there it is, right? 0.417. So our calculation matches there. So now that we're looking at these tables, right, is that any specific time that we have here, right? The time we have at 0 hours, at 6 hours, at 12 hours, these are what we call instantaneous time, right? So any specific time is what we're going to call the instantaneous time, right? Instantaneous time. And at time zero, we'll just say it's zero because we do have, oh, right, where it says time zero, that instantaneous time there. So at time zero, this is what we're going to consider our initial rate, right, at time zero. So let's bring this, I'm not going to scroll up, I'm just going to rewrite the formula or the reaction that we had here. We're looking at decomposition of hydrogen peroxide. And we get some water, some oxygen gas. So when we're looking at this, we can also now consider what we call relative rates of reaction. Right? So we have relative rates of reaction, right? Relative rates of reaction. So not only do we have the reaction for what's being consumed, but also reaction rates for what's being produced, right? So there is some relationship between the reactants, rates of the reactants, and the reaction rates of the product. And we use some stoichiometry in order to maybe understand um, these relationships they have. So these relative rates of reaction. So as we're consuming the reactant, we see those as we use a negative value there. So we have negative change in concentration of hydrogen peroxide over some change in time. Now, if we use these stoichiometric values here, and we'll even put a 1 right here, just for the sake of understanding here, is that this rate of reaction here is equal to, and we're going to use this here. We'll say that 1 over 2. So we're taking this coefficient, and now we're saying 1 over 2, right? 1 over 2. So this is equal to, and if we come out with the product here, we'll say the change in the concentration of water over, and that is, yeah, the change in the concentration of water, let me take a look at something. Yeah, over some amount of time. And again, we're using that stoichiometric value, and that this is equal to, and note it, because it's a product, I didn't put that negative symbol out there. So the reaction rate for this would be a positive. We didn't put this right. We didn't put that negative symbol there. So here, this is going to be equal to the change in the concentration of oxygen. I should be putting this here, brackets, concentration, over some change in time. Right. So we kind of look at this like the rate of disappearance, right? So the rate of disappearance of, right? It's really annoying when my mic cuts out. So look at it as the rate of the rate of disappearance of hydrogen peroxide is twice the rate of appearance of oxygen, right? Because there's 2 moles of hydrogen peroxide, I only have 1 mole of oxygen. So the rate of so H2O is disappearing twice as fast as the rate of oxygen that's being produced. So we use these stoichiometric values in order to come out with these reaction rates, or these stoichiometric factors, as we'll call them, right? So I'll write that over here. I'll put that off to the side. Stoichiometric factors. So let's look at them. Let's look one that's more complex here. So let's take a look at we'll say 5 bromine. All right. So if we want the stoichiometric factors here, the relative rates of reactions, right? We need to remember that all of the reactants, right, is we need that negative in front of there. So we're going to say, we'll say the change in the concentration of Br minus over some amount of time, and we'll put a negative symbol out there, is equal to the negative change in minus over some amount of time. And this is also equal to, uh, oh, I forgot one thing here. We're going to put 1 over 5. We'll put, for hydrogen, 1 over 6, right? Because we see the 6 here. Change in concentration of H plus over some change in time. And this is equal to negative symbol because it is a actant. This is equal to 1 over 3 change in concentration of Br2 over some amount of time, which is equal to 1 over 3 change in concentration of water over some change in time. So I have all of these stoichiometric factors if we're needed to calculate any of the rates of reaction, right? Our rate of reaction, like all of these stoichiometric factors are used to determine rate of reaction, right? So those are all rates of reaction. Look at this. My rate of reaction is equal to some change in reactant, the concentration of the reactant, over some unit of time. So all of these stoichiometric factors, all of these here can determine rates of the reaction. So we use this balanced formula here in order to determine all of these rates of reaction. So the rate of reaction is equal to negative 1/5 times the concentration of bromine over some amount of time. And these are all rates of reaction that we see here. So let's look at another one here. How about we use the decomposition of ammonia. So decomposition of ammonia, this will break up into nitrogen gas, plus it'll break up into some hydrogen gas. Balance, 2 here, put a 3 here, 2 nitrogens. Yep, I think we're balanced here. All right. So at the rate of decomposition here, the rate of decomposition, so we'll say the rate of the decomposition of NH3 at 1150 Kelvin. Now, all of these reaction rates, um, we didn't introduce, no, we'll talk about K. This is Kelvin here. We'll talk about a different constant here, not Kelvin. So we'll say the rate of decomposition of NH3 at 1150 K, 1150 Kelvin is, the rate of reaction is 2 times 10, no, 2.10. We'll say 2.10 times 10 to the minus 6 mole per liter per second. What is the rate of production? If we know what the rate of decomposition, and this is rate of reaction, this is the rate of decomposition. Here's right that here, well, not the rate of decomposition, but if we're talking about the rate of decomposition, we're looking at this, right? If the rate of decomposition here, right, is that this is going to, concentration is going to decrease, the rate of decomposition means that I'm looking at this being some negative value here. So the rate of decomposition here, the rate of decomposition, we'll take a look at this, we'll say 1 over 2 times the change in the decomposition here, the concentration here, over some amount of time, right? And this is equal to the change in concentration of N2, some amount of time, and this is equal to free concentration of H2 over some amount of time. Well, we know what the rate of decomposition is because it's given to us. The rate of decomposition, here's the reaction rate. Oh, and I did miss a negative sign here. Can't miss those negative signs. So we know what this equals. The rate of decomposition is equal to this. The rate of decomposition is equal to this. Now, if I know what that value is, I can rewrite this now. And this is where this understanding needs to come into play, is that if I know what this value is here, this rate of reaction for the decomposition here, I can write this, and I understand that this is equal to this rate is equal to this rate. Well, we can say negative 2.10 times 10 to the minus 6 moles per liter per second is equal to over some amount of time, right? So this here, it's asking you to find the rate of production. This is the rate of production. Okay, well, you know what? I didn't put divide by 2. I missed it. Here we go. Divide by 2, right? Because 1 over 2. So here, let's calculate what that is. So we're going to have negative 2.1 times 10 to the minus 6, divide by 2, and this equals
Wouldn't it be negative? Oh yeah,
All right. Moles per liter per second. All right. Let's take a look at uh, let's take a look at the next one, and we can do the same thing, and we'll say negative 2.10 times 10 to the minus 6 um, is equal to 1 over 3. So this changes just a little bit here. Oh, let me see here. Yeah, there we go. We're going to have change in the concentration of H2 over some amount of time, right? Well, we have to take care of this 3 here, right? So if I multiply this side by 3, I now have to multiply this side by 3. And then our value simply becomes calculation for this, anybody?
I got negative 3.15 times 10 to the negative 6.
All right. Let's see. So now we'll talk about factors um, that kind of affect these reaction rates, right? So we're um, just now learning and understanding these reaction rates. So how fast a reaction happens? Esmeralda got 1.05 times 10 to the minus 6 for which one? The one we just did?
That was the last one. It's okay.
La okay, let's see. So we got
Yeah.
3 times 2.10 times 10 to the 2. Yeah, I don't know what happened. I got
And that one's
3.1.
for the negative 2.1. This previous equation.
Oh, oh, I
On the
see.
right
Oh,
hand
no.
side.
Okay, I see. I see. Yeah, and we did end up getting that answer?
Yes.
Okay, perfect. Okay, thank you. I didn't even see it there. A little late on the chat.
Mm.
All right, so factors that affect rate. So not all reactions happen at the same time, right? Is that there's different factors in play that can increase reaction rates, that can decrease reaction rate. So what we'll talk about next are just simply factors that affect reaction rates. So this could simply be just the physical state. Physical state will affect the reaction rate. Temperature, how hot something is, how cold the reaction is, um, how hot the reactant is, how cold the reactant is, right? So temperature has an effect on reaction rate. Concentration has an effect on reaction rate. We can insert a catalyst that'll affect the reaction rate. So as far as maybe just physical state can affect a reaction. If we take a look at this reaction here, let's take a look at iron. So we'll say iron solid, put that into some hydrochloric acid. So here, if we put this into some aqueous, right? Put iron into some hydrochloric acid, we're going to get this reaction. But physical state of the iron, the physical state of the iron can really change the reaction rate. If we put this into a test tube, let's say I put this block of iron into a test tube, right? And then I'm going to put in some HCl into it. It's going to dissolve it, right? But what's going to happen faster? What if instead of that block of iron, what if I chop it up into bits? What if I chop it up into bits? Well, because there's more surface area, because I chopped it up into these big chunks here, right? Is that this reaction is going to happen faster. Faster because there's more there's more surface area. Is that the hydrochloric acid is going to be able to get to a lot more of this iron in order to dissolve that. So simply just physical state can absolutely increase the reaction rate. Going from a solid to liquid, right? What if we somehow manage to liquid, get some liquid metal here, and now we have just a bunch of these molecules because it's liquid, right? Well, that's going to be even faster, right? Uh, if we're talking about liquid versus solid, even versus ground solid. I'll even put ground solid here versus up a ground up solid, right? That this liquid's going to be even faster than that. But again, because there's simply just some more surface area. So that's one way we can increase the reaction rate. Another way we can increase it is by temperature, right? Temperature will also increase or decrease the reaction rate, right? So we're thinking about adding energy, right? So if we add or remove energy from these reactions, right? Um, Temperature. When you guys put food into the fridge, right? So think about a fridge, right? Why is it that you don't put your refrigerator up to 70 degrees, right? Why don't you put your refrigerator up to 80 degrees, right? Because the cold slows your spoiled food, right? So think about a fridge and we put it that we make it colder uh, to slow food from spoiling, right? And if you really don't want it to spoil, where else do you put it? Well, you put it in the freezer to make it even colder, right? So what's going to happen if you turn your dial up in your refrigerator up to 80 degrees? Well, your food's going to go. It's going to spoil a lot faster. So temperature plays a rate a role in the rate of reaction. Concentration. Concentration also plays a role. Concentration also plays a role. if you didn't already know, some older statues um, have a lot of calcium carbonate, right? Uh, they have a lot of calcium carbonate in some older statues, and you'll notice that some of them really start to um, decompose, right? And they decompose because what happens is in the air, we get some sulfurous acid in the air, and that can decay the carbonate that's in some statues, right? So this is the reaction for that, and we'll say we get some calcium, uh, plus we're going to get some carbon dioxide, plus we simply just get some water from that. So this would be gas, this liquid. This ends up being aqueous, just washing away. And just so we have some reference here that we're talking about statues here, not statutes, statues. I'm glad I wasn't an English major. Statues. Well, concentration, the concentration of sulfuric acid can either um, increase or decrease this rate of reaction. If we increase the concentration here, we're going to get more sulfuric acid. So what happens is that in the air, this is just in the air. So in the air, we have this gas, right? And the more we have of that in the air, the higher the concentration. Well, I'll put gas here, right? Because we have water molecules in the air. Um, so here, the more concentration, the more of this we have, the increase we're going to have here is that this is going to really increase the concentration of our H2SO3, that's the sulfurous acid, and we're going to get an increase in this reaction here. So constant rate, if we have a small amount of SO2 in there, the sulfur dioxide, if we have a small amount in the air, that concentration goes down, and we're not going to have so much. Right? If we increase the concentration here, we're going to decrease the concentration here, and we push the reaction this way. Right? If we decrease that concentration, we increase this concentration, which means that this reaction will shift this way and slow that decay, right? So the concentration can really play a role here. The other one would be, I think the last one would be what we call catalyst. So a catalyst, so this is increasing. So this will increase the rate of reaction by lowering lowering activation energy. By lowering activation energy. Uh, in short, what happens is just it provides an alternate path. So by lowering the activation energy, what that's simply just saying is that we're just providing a different path. So I think there's we should have a page in here. Let's see. Yep, there it is. Right. So we did see a different pathway. We see that, shortest distance between 2 points is a straight line. Well, right, we're shortening the path. So by putting in a catalyst, we lower the activation energy, the energy required for the reaction to take place, and that increases the rate of reaction. So we have this what we call alternate path here. So we have catalyst, concentration, temperature, physical state. All these will play roles in how we increase or decrease these reaction rates. So rate law. So what we're going to talk about now are what we call rate laws, right? So what a rate law is it's a mathematical expression that's going to describe the relationship between the rate of the chemical reaction and the concentration of those reactants, right? So it's simply just, um, what, I won't use those. Rate laws are simply just a mathematical expression. So mathematical expression to describe the relationship between, well, we'll say the, not between, but the reaction, how should we say this? Mathematical expression to describe the relationship of the rate of a chemical reaction and the concentration of the the reactants. So concentration of the reactants. All right. So what a rate law is, there's a basic structure for rate law. There's just a general expression that we can use here. So we say that the rate is equal to K times the concentration of A, and then we're going to put here. This is the what we call the reaction order, right? And I don't mean order by you go first, you go second, you go third, right? So here we'll say multiplied by the concentration of B times the order of that concentration. And we'll get into, well, I'll describe what order is. I mean, don't worry about it. L, M, N, we can use O, I think P, I think the B book uses P. And then I'm just going to simply just put dot, 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 because this can keep going and going. So the concentration of D, and again, let me put, yeah, let me just put one more here. Just, it doesn't even matter which variable you use. We can put, I don't know, T or something, right? I'm just put dot, dot, dot. So rate is equal to K times the concentration of A to whatever order that reactant is times the concentration of B to whatever the reaction order is for that. And K is equal to what we call the rate constant. Why is it? I got a dead spot? Interesting. Why did it disconnect? I have to steal my wife's. Hopefully it's not dead. Sorry, but my Apple Pen here is finger. Oh, let me just pause. Let me pause the video real quick while I fix this. Let's go back to reaction rates real quick before we move on. We did have some negative values. Oh yeah, so uh, yeah, when we're looking at this instantaneous rate here, um, that here, uh, uh, even though we're coming out with negative rates, we don't use the negative rates of reaction here. Just like we don't use negative absorbance or anything like it. We just use the positive value here. So even though it says negative, we're going to use the 0.105, for the reaction rate there.
So they're going to always be an absolute value. It's always going to be.
Yeah. So for the reaction rates, yeah. So we're not going to have we won't have a negative reaction rate.
Okay.
Let's see here. All right, so let's go down to the rate constant. So we're back to the rate constant. So the rate constant. So the rate constant. So this is specific. This is very specific. So K is specific to the reaction, meaning that different reactions are going to have a different rate constant, and they're also specific to temperature. So it's specific to the reaction at a temperature, right? At a certain temperature. We change the temperature, the rate constant changes. If we change the reaction, the rate constant changes. And these values here, M, N, P, T, these are determined, must be determined experimentally. You can't look at a reaction and know what those values are, right? It's not like the rate constants or the constants we've seen before, where we just use the molarity and go, oh, the molarity, I'm going to use that as my superscript. That this is not the same thing. That these values are determined experimentally, and what these values are what we call rate order. Right? So rate order, we can have zero order, first order, second order, so on and so on. Let me clean this up a little bit. Just put dot dot dot. First order, third order, fourth order, whatever that reaction seems to be. But again, they're determined experimentally. So if I give you a reaction that looks like this, here's some hydrogen gas. We'll add some nitrogen monoxide to it. Um, we'll get some dinitrogen monoxide. Plus, we'll get some water uh, gas out of that. Uh, yeah, I think we're balanced, right? So uh, don't look at this here and go, okay, I know the reaction order for that. Like that's not how it's determined. Is that we don't look at that value there. Um, so for right now, I will give it to you. We'll be able to figure it out, but we need a table in order to figure that out. Hey, buddy, shush. We need man. I can. You guys, I don't know. I'll just after class I'll show you my. I have a couple Great Danes here, upstairs. That's the one that's barking. He gets a little. Um, he's a tattletale. When he barks like that, when you hear him barking like that, he's tattling because I have a little rat dog that is playing with a toy he wants to play with, right? Uh, my Great Dane is the sweetest dog you'll ever meet, and he, but he gets bothered because my little rat dog is playing with his toy. So when he's barking like that, he's kind of tattling on him, saying, "Hey, mind giving that up for me?" All right. But anyways, so here I'm going to give you um, the rate law here. So the rate law here. So this is the rate law. The rate law here is equal to K. And we only use the reactants for the rate law here. So here, and I'm going to put 2 up here, and then I will put hydrogen gas over here. So this is the rate law, right? And this is what we're going to consider second order, but not because of the 2 that's there, right? And H2, so it's second order because of this value here. Because that's a 2, it's second order. And because the hydrogen has an imaginary 1 here, that this is going to be considered first order. Then we have to determine something that we call overall reaction order. So we take 2 plus 1, and we get 3. So the overall reaction order here is 3. I get 2 from the nitrogen monoxide. I get 1 from the hydrogen. 2 plus 1, 3. Very simple math, right? Let's say we did this at a different temperature, different concentration, and I'll give you a new rate order, a new rate law. So we'll say this time the rate is equal to our K constant here. So our K value, we'll say, how about just this? How about NO? And we'll say 2. All right. So here, NO is second order, and we say that the concentration of H2, well, there's none there. That is 0 order, right? That's just going to be 0 order. So the overall reaction order here is simply just 2. So I'm going to need to go to a different table. I need to go to, is that, yep, it's still open. Perfect. Nope, not open. Let me reopen it. Chem. We're on page, what is it, like somewhere around here. Should we use this one? Should we use a different one? We'll use this table here. All right. So we look here and we need to determine the order, right? We need to determine the reaction order for NO03, NO2 plus O2, right? We need to figure out this reaction order here. So I'm going to kind of be flipping back and forth here. So we need rate is equal to K times the concentration of, is it NO and O3? NO and O3, right? And we need this M and this n over here. So what we need to do is figure out what m is equal to and what n is equal to. So this may seem a little bit um, uneasy, maybe a little bit confusing at first, and hopefully you'll catch on to looking at this. So the rate order is determined by this experimentally, right? So first order, second order, third order, and so on. When we look at the concentration, let's look at the concentration of NO first. So you'll see in the first five here, the concentration of NO didn't increase in the first three trials. Trial number one, trial number two, trial number three are all the same. So what we need to do is we need to compare the concentration between 3 and 4, the concentration between 3 and 5. Because if we look at O3, the concentration of O3, ozone, concentration of ozone didn't change. So that's a constant there. We don't want to determine these with different concentrations here if we don't need to. So we're going to take a first look at 3 and number 4. If we we literally just double the concentration from 3 to 4. We went from 1.00 times 10 to the minus 6 to 2.00 times 10 to the minus 6, and we doubled that concentration. So if we double that concentration, let's see what happened to the rate. 1.98 times 10 to the minus 4, we double the concentration, and we get 3.96, which means that we doubled the rate. If we double the concentration, and we'll say M, we doubled the concentration, and as a result, we double the rate. All right, let's take a look at another one. Not just going to take a look at that one, but let's take a look at another one just to verify here. Here, I'm going to look at 3 and 5. I triple the concentration from 1.00 to 3.00. I triple that concentration, and what happened to the rate? Well, I got 5.96. So that's also tripled. So because they're increasing and at the same rate, we double the concentration, we double the rate. We triple the concentration, we triple the rate. That means that this is first order. So the concentration of NO, so this is simply just first order. And we can put a 1 there. So now let's take a look and see what happens with ozone, the O3. Trials number 1, 2, and 3 are different, but here, now we can take a look at what's happening here. All right. So 3.00, and if we double that, concentration, what happens to the rate? Did we double the rate? Yeah, 6.00 times 10 to the minus 5, and you can check in your calculator to make sure that this is true. But if we take 1.32 times 10 to the minus 4, and if we divide that by 2, I get 6.6 times 10 to the minus 5. So in fact, that did double. So if we double the rate, we double the concentration, we double the rate. All right, well, let's see what happens. If we triple the concentration, 9.00, well, do we triple the rate? 6.6 times 10 to the minus 5. And if I triple that, I get 1.98 times 10 to the minus 4. So again, we're in another situation where n, we double the concentration, we double the rate. We tripled it, triple the concentration, we triple the rate. So as long as it's staying in that one-to-one fashion there, right? Oop. As long as it's staying in this one-to-one ratio, is that this becomes also becomes first order. That also becomes first order. All right, so again, these are determined from experiment, right? Is that we need a table in order to look at this. So I think we'll be able to do one here before. Let me pick one out here. We'll save that one. That one's a little more complicated. We'll save that one there. Yeah, let's do this one. Let's do this one here. Let me see. We'll work on this one here. Um, we'll verify, make sure we get these answers right. So here, if we take a look at this table here, so the reaction we're looking at is, hey, come on, Morgan. CH3, CHO, gas, plus and then we're going to get some CH4 gas. We'll get some methane from that, and then we're going to get some, what's it, CO2? CO, just some gas. All right, so here, let's take a look at this. uh, we only have one to deal with, so there's only one reactant to deal with, so that's not bad. If we take a look at this, let's see what happens here. We go from 1.75 times 10 to the 3, and if we double that to 3.5, we go from 2.06. So we go from, if we double the rate, 1.75 times 10 to the minus 3, and if we double that rate, we get 3.5 times 10 to the minus 3. But as far as the time goes, the rate, we got 2.06 or 05, 2.06. 2.06 times 10 to the minus 11. And what happens to this rate is we go all the way up to 8.24 times 10 to the minus 11. Did that double? No. If we doubled it, it'd be 4.12. Did it triple? No. Didn't even triple, right? This quadrupled. So this quadrupled. So by doubling the rate, we quadrupled the rate, right? We quadrupled the rate. So this is what we consider uh, when we quadruple the rate, and I'm going to write that down here so you guys have that in your notes. We quadrupled the rate. That this is what we're going to consider second order. So this is second order when we quadruple the rate. Quadruple the rate, second order. Double the concentration, quadruple the rate, second order. So here, my rate law is going to equal K, concentration of CHCO here. Right. So we're going to use the initial rate here. We're going to use what we call the method of initial rate. So I'm going to write that here. We'll finish this and I think we're good to go. Method of initial rate. So our method of initial rate, because we're gonna solve for k. So if we rearrange this, we can say that k is equal to the rate over the rate order, right? So what is this going to equal to? Well, we know what the initial rate is. The initial rate is simply just 2.6 times 10 to the minus 11 moles per liter per second. So this translates into 2.06 times 10 to the minus 11 moles per liter per second over the concentration, because we're using the method of initial rate here, over 1.75 times 10 to the minus 3 squared. And let me put units in here before we do that. So somebody calculate that and give me an answer. Because we're squaring that, it means we're squaring the moles, we're squaring the liters, so our units end up being seconds still, so we're good.
I got 6.72, or well, 6.73 times 10 to the negative 6.
All right, sounds reasonable. 6.73, 6.72, however you're rounding there. Um, right? And that's just using the method of initial rate there. So quadruple the rate, we got second order. Um, we'd get, so we've covered first order, we've covered zero order. I think we'd have to go like, I don't even know, like if the rate goes to like times 16, so this would be third order. So if we see something like this, just kind of an example. I don't think you're going to see anything in the homework, not even on the exam. On the exam, I'd be using first order, second order. I don't think I'll be using third order. But this is what third order would look like. Times 10 to the minus 11. Third order would be to the 16. We have to like not quadruple it, but let's see, 2.06 10 to the minus 11. Oh, it'd go up. It'd just like 2 to the 16th or 2 to the fourth. That goes to. I think it ended up being like 1.6. Yeah, it's you know what? No, we're not even going to worry about third order. I'll make sure that I'll verify that the homework doesn't have anything in the third order. Third order goes really high. That's what third order is, a really fast reaction. Like that's a pretty fast reaction. So we're just going to deal with first order, second order, zero order. I'm not going to really worry about anything that's third order. So for the exam, we're just going to worry about quadrupling the rate or doubling the rate, or if the rate doesn't change at all. So we'll have first order, second order, and zero order that we'll worry about for this chapter here. So I think we're done here. Let me
When we
stop the
have zero
recording.
order,